Swayam Prabha. Digital India. Educated India.
Here it is. This is what I wanted. You see, here you have these blue rays which are coming parallel and they are traveling, parallel to the principal axis. After reflection, all these blue rays, where they envelop, okay, that is exactly this, tree-shaped thing that you see. That's what you see. And what are these points? Those points are actually the respective foci, approximate foci, if you take only a small portion of the mirror. But you see, as this piece moves, okay, these foci are also moving, okay, because if you make the angle theta large, sin theta is no longer theta, cos theta is no longer 1, okay, so your formula is wrong. But if you did not make that approximation, and if you have the patience, you can do it. You write out, you will get a curve, which will involve sin theta, cos theta. You draw the curve, you will get exactly this blue curve. You can really do it. Okay, so that's how this blue curve comes. So the point is, why does this blue thing show up? It shows up because it's the envelope of reflected rays. Okay, it's the envelope of. So what is happening? This blue thing is at every point of the blue thing, it is, you have a tangent which is a reflected ray. Okay, that's what I want you to understand. Alright, and the envelope of the reflected rays, they form this blue shape. Okay, and now you see this kind of a thing which you get after reflection of rays, the envelope of that is called a caustic. Okay, and caustics, one of the most important examples of caustics are rainbows. So the way you get a rainbow is, you see, you have, sun rays coming in a certain direction. There are water droplets that are suspended. But you see, this is a three-dimensional thing that's happening. So what happens is that there is going to be rays that are going to get refracted. Okay, part of them are also, some of them are even totally internally reflected. Okay, now what will happen is that these refracted rays, now you are refracting in space. Okay, so what you will get is the envelope of a family of rays in space will be a surface. It will not be a curve. Okay, in the plane case you will get a curve, but in space you will get a surface actually. So what is happening is you get something like a spherical surface, and it's the perpendicular cross section of that you are seeing in your eye, and you get all those colors. You are only looking at a cross section of this shell. Okay, all right, and this is again a caustic. It is gotten as the envelope of refracted rays. Okay, so rainbows are examples of caustics. So now let me come back to what I told you. You see, if you look at where is this? So here you see what is happening here. If you look at this picture now, all right, I want you to understand the following. So maybe it's not clear in this picture. I think I should use the other one. Here it is. So now look at this picture. You see that the red ellipse is your ellipse, original curve, and then you draw the black normals to it. Then you get this blue curve which is the evolute. But do you see that the evolute is actually the envelope of the normals? the blue curve is gotten, you look at every point of this blue curve, why it shows up is because it is an envelope of lines. And what are the lines? The lines are the normals. So what you see from this picture is that this blue curve is showing up because it is the envelope of the normals. Okay, so you get the following thing: the evolute, which is the locus of the centers of curvature, is also the envelope of the normals. Okay, so what shows up is always the envelope. In the coffee cup, what you see, the bright light, the shape that you see, that is actually the envelope of the reflected rays. It's a caustic. When you see a rainbow, it is the envelope of refracted rays. That's your rainbow. They are all envelopes. Okay, and this is a case of that. Okay, and physically, why are you able to see it? See, if a single light ray passes like this, I'm not going to see it. Okay, but if several light rays coalesce at a point, then at that point it will become very bright. So what is happening on the coffee cup is that at each of those points, too many rays are converging at those points, because that is the envelope. So that's where all the tangents come closest. And at that point, you see what will happen to the intensity. The intensity will be very high, because many light rays are converging at that point. At each of those points, the density of light rays that is convergent is very, very high. That's why at those points you see extra brightness. That's how you see it in the first place. It shows up. Okay. And so I wanted to understand that this idea of these physical phenomena are happening because this idea of light rays coalescing on a locus mathematically is the same as looking at the envelope. Okay, and if you take a curve, you can go to its evolute in two ways. One is you trace the trace the centers of curvature. That is one way. The other easy geometric way is you simply draw normals. See, finding the circle of curvature and the radius of curvature and center of curvature is a complicated thing. Okay, so if I want to find at a particular point of a curve, if I want to find the circle of curvature, center of curvature, radius of curvature, that involves some calculus, some formulas are required. But to plot the locus of all the centers of curvature, which is evolute, I don't need anything. All I have to do is just blindly draw normals. Okay, automatically the normals will coalesce and the evolute will show up. You get the envelope immediately. Okay, so that is what is happening here. So here also in the case of the nephroid, you can see that close to the nephroid you see the accumulation of all the normals. So that this blue nephroid is actually the envelope of all the normals to the red limacon. All right. And similarly, in the case of the sine curve, you see this blue part, these blue curves, they are the envelopes. Okay, they are the envelopes of the normals. All right. So okay, so this is something that's interesting. I wanted you to know. There is math connected with all this, but you need to. So there is this subject called differential geometry, where you actually do prove these things properly using calculus and analysis, okay, and topology. All right. Now, so you can go from a curve to its evolute. So this is the transformation. Namely, you start with the curve, and then you can go to its evolute. And how do you get the evolute? Either it is the locus of centers of curvature, or it is also equal to the envelope of the family of normals. They are the same. All right. Now, so this is a transformation. Now, nice thing is in mathematics are that you can make a transformation. Can you reverse it? Okay. Can you reverse a transformation? All right. And so that is a way of reversing it. It's not accurate, but you can reverse it. And that is what is called as taking the involute. So you can come back by, so let me write the following thing. So curve inverse process. You can go from the curve to what is called its involute. So, okay. So there is so these are transformations of curves, all right. And you should understand these transformations are not ordinary transformations. They are kind of complicated because they involve some calculus. And you don't get the same curve always, you get a different curve. Of course, in the case of nephroid and asteroid, you got the same symmetrical case, you got it, but otherwise you get completely different shaped curves, okay. And there is this inverse process which is called forming the involute of a curve. So what is this involute of a curve? Let me tell you, all right. So there was, is there a break or something? At 11, is it? Okay. So I wanted to know, because I started a little late, right? I started at 9:30. Yeah, so I think maybe I will continue for another hour. If you want to have a cup of coffee or something, you can break and then come back. It's over? Break is at 11, is it? No, but 11 I won't stop. So, is it, can you check if you want to have a break now or we'll go ahead? Pardon me? So I thought, no, but after 11, is there something else? You are leaving for a project, is it? Okay, then I will not break. Okay, so because I have to say something. So maybe I'll just say this and then I will stop. So you see, so you do the following thing. What you do is that you take a curve, okay? All right, this is some curve, okay? Now what you do is you fix 2 points on the curve, P and Q, all right? And you put a string on the curve, okay? So here is this, here is this red string on the curve, all right? And what you do is you fix one of those points, okay, keep that point fixed. And then what you do is that you draw the string from P, okay? So you can imagine that the curve is like this. There is a piece of the curve, and then one point I am fixed and the other point I am pulling it out, okay? Now if you pull it out, it's going to trace another curve. You have to gently pull it out. You assume the string is taut, that is, it will not expand or contract, okay? And you are just supposed to unwind, okay? It's like unwinding this curved string with the point or the other point Q fixed. So what will happen is that you will get a curve like this, okay? And so if this is the curve, so let me just not put Q symbols. This is the curve and this is the involute. And you see, at every point what is going to happen is, you just think about it, when I just pulled it out, okay, then you see this this distance will be the same as this distance. That is the string that is pulled out, okay? And you also see that if you think about it for a moment, you will see that for the involute, say here at this point, you see at this point, this will actually be normal, okay? And for the curve at this point, it is actually going to be a tangent, okay? And so if you think about it, this is what is happening. Okay. Okay. So this is how you get the involute. And you must understand, see, when you just pull it out, okay, when you just pull it out, you see you are, the string is taut, therefore it should be, at the minimum distance, and that's why you get the perpendicularity. Every point on the involute is at minimum distance to the point up to which you have pulled the curve out, okay. So and when you pull it out, at that point, the string would be the tangent to the original curve. Do you see that? I mean, are you convinced about this? See, either if you look at the motion like this, it is actually pulling out. Okay, but if you put it the other way around, it is actually you're winding the string. So this is this. If you do it like this is unwinding. Okay, and if you do it like this, then this is going to be winding. You are just winding or unwinding the string, but this fixed point, I mean this moving point which was originally at P, that traces the involute. Okay, so is this picture clear to everyone? Yes.
So basically we are treating this curve as an evolute of another curve, and we are taking the involute, pretty much.
Say that again.
We are treating this curve.
Which curve?
No, the curve that we took and drawing tangents to it. The original curve that we are taking the involute of, we are treating that curve as an evolute of another curve, pretty much.
Very good. Yes. So you see, very good. So you see that. So you see what is happening. So you have this original curve, then you have this involute. Now what happens is the involute has normals, and these are nothing but the tangents of the original curve. The normals to the involute are the same as the tangents to the original curve. Okay, so if you take the involute and take its evolute, okay, you will get the envelope of the normals to the involute, but that is the envelope of the tangents to the original curve. The envelope of a tangents to the curve is the curve itself. So you see immediately that you have reversed the process. Do you see that? You have reversed the process. So basically, so from the involute, if you go back and take evolute, you get back the curve. Okay. So this is this process reverses it. All right. So let me write this. You start with the curve, then you take its involute, and then you again take the evolute, and you will get back the original curve. Okay. Now you can do it the other way around. What you can do is you start with the curve, first take the evolute, and then take the involute. Okay. And there something is going to happen. See, the problem is that when you take an involute, you have to fix a point, and there is a fixed point, and you are starting from another point which you are moving. Okay, but these points can change. You can get many such involutes for a curve. For a curve, there is only one evolute because it's uniquely defined as the locus of centers of curvature. But if you start taking involutes for a curve, you can have many involutes. The question is, how are all these involutes related? So here is something interesting that is going to happen. They give rise to what are called as parallel curves. Okay, so if you start with the curve, take the evolute, and then take any involute. Okay, and when I say, I will be very careful. I will write an involute because there can be many, but there is only the evolute. Okay. Similarly, here you have the evolute and you take an involute. All right. The point is that what will happen is you get what is called as parallel curve. You get what is called a parallel curve, and you physically you can think of it as just what is a parallel curve that looks like the same curve and it is displaced by the same distance in the correct direction. Okay. So how do you think of it? See, suppose you have a curve gamma. Okay. So let me again not use any notation. This is my original curve. What is a parallel curve? So what you do is at every point you draw the normal and then go by a certain distance d, and you take this new point. Okay. Then at this point again you draw the normal, again you go by the same distance d, you get this new point, and then you do this. And if you do this, you see you will get a curve like this. This is called the parallel curve. The parallel curve is you take the original curve at every point and then you move by the same distance in the normal direction. That's very, very important. So you get a curve which looks like the original curve. Now the beautiful thing is you can easily see if you take a line and you take a parallel curve to a line, you will again get a line. Okay. If you take a circle and take a parallel curve, you will get another circle. Alright. But these are the only two curves for which these things will happen. Okay. The interesting thing is that for all other curves, if you take a parallel curve, you will get a curve which is completely different from that curve. Okay. So your question, yeah.
Sir, aren't involute and evolute the same curve? I mean, the same in, they are just the same function, but just tilted 90 degrees.
It can't be, no, because
Because we are just drawing parallel lines to the curve for the involute, and we are taking the perpendiculars for the evolute.
no, it's not just it's not just about the lines; it's about the envelopes.
No, the whole curve should be perpendicular to each other, right? Involute and evolute. Shouldn't that be?
No. See, when you be very careful, when you say two curves are perpendicular to each other, that means there must be a point of contact, and at the point of contact, the tangents should be perpendicular. See, that way, you take any curve anywhere and some other curve, and you just draw one line, at one normal to this and one tangent to the other, which are perpendicular. They could be at one point. It can happen.
Like every single point I'm saying.
No, that's not the way to think. I mean, that will not give you, that's not a unique definition. You can think about it. See, if you think of one curve as being another curve rotated by 90 degrees, then essentially it should look the same. See, if I take an ellipse and I take its evolute, then I don't get an ellipse, I get an asymmetrical asteroid. I get a completely different curve. So you see, when you go from involute to evolute, the curve is completely changing, except for special cases. Okay, so you have to be very, very careful. There are examples I have shown you, nephroid and asteroid. The evolute again gives you a nephroid and asteroid of scale size and which is rotated. But in general, the involute and evolute, they are very, very different. Okay, so here is the interesting thing. If you start with a curve, you can define what is called a parallel curve. Parallel curves for straight lines, parallel curves to straight lines are just parallel lines. Okay, and parallel curves to circles are simply concentric circles. There is no problem. But here is the interesting thing. You take any other parallel curve, okay, in general it will be a completely different curve. For example, if you take a ellipse and take a parallel curve to an ellipse, it will look like an ellipse. But if you write the equation, it will not be an ellipse. Okay. Similarly, if you take any conic, parabola, ellipse, hyperbola for that matter, draw a parallel curve, okay, and write its equation, it will not be second degree. Okay, you will get some higher degrees. It looks like that, but it is not that. Mathematically, it's different. Okay, so this is somewhat hard to understand, but the only way is you have to write down the equations and see that the parallel curve is very different from the original curve. Okay, so the moral of the story is that you start with a curve and you take the evolute and take an involute, you will get a parallel curve, but there in special cases you can get back the original curve. Okay, if you take a particular involute cleverly, you will get a special curve, and I will give you an example of this. And a standard example is the very important thing is that is this very important curve called the cycloid, okay, which is the path traced by a point on a circle rolling on a line. Okay, and with the cycloid, what happens is that if you the nice thing is if you take the evolute of a cycloid, you will again physically get the cycloid, same cycloid. Okay, and if you take the involute at the top points of the cycloid, you will again get back the same cycloid. So you see, so that's a very special curve and it has got a lot of physical significance. So example is you take cycloid. So let me write here, this is not mathematically of the same type as given curve. Okay, except for straight lines and circles. Okay, so cycloid. So let me show this. So the cycloid will be like this. Okay, and basically you are starting with so here is my circle, and here is a circle again, and here again is a circle. Okay, and you see this is the point P, and this point is moving, the circle is turning, and it moves all the way. Here it is at the topmost position, and then it further moves and comes back to this. Okay, this is your cycloid. Okay, and here is the interesting thing. For this cycloid, if you draw the evolute, let me draw the evolute. The evolute will look like this. Okay, so you take the same distance. Suppose the circle radius is A, then this length is 2A. Okay, then and if you want, I again take the same distance 2A here. Okay, and what will happen is that the evolute will be like this. So let me draw this. Oops. See, the evolute is again a cycloid, same cycloid, but it has been displaced. This is the evolute. Okay, it is the same cycloid. You push it to the right by this distance, which is half this distance, and then you push it downward by 2A. If you make this two translations, okay, then you will get this evolute. So the evolute of a cycloid is again a cycloid. And what about involute? That's also the same cycloid. If you take the correct involute, what involute you will have to take is this. Okay, so you take, so let me show you, you take this, take a piece of string like this, starting from here to here, okay, and pull it out, and you will get this cycloid. Okay, and now if you continue it, you see the involute will again be a cycloid. This is the involute. Okay, so both the cycloid is a special curve for which it's its own evolute up to translation, and it's also its own involute if you take the correct involute. Okay, yeah.
Sir, what do you mean by a correct involute?
No, correct involute. See, involute depends on, you have to just take a piece of string on the curve, and you have to fix one end, and you have to unwind the other end. Right? That's what you have to do. So the point is, so it depends on how much length of string you are taking on the curve, and which point you are keeping fixed. So if you choose another point, then you will get only a parallel curve. So for example, so let me show you this. Suppose I chose only this portion of the string, say from here to here. Okay, and if I pulled it out, I will get this. Okay, and if I chose something bigger, so let me show you something else. Suppose I chose up to here, let us say, all the way from here to here, okay, and pulled it out, I will get something like this. Now the interesting thing is that this green and this orange, they look like cycloids. They are parallel to the cycloid, but they are not cycloids. If you write down the equations, they will be mathematically completely different. That's what is amazing. So the curve that looks the same and is also mathematically the same, when you take parallel curves, that happens only for straight lines and circles. Okay, otherwise you get curves which look the same, but they are not the same. And this is of great importance in computer vision, all this, animation, because I want to show some, see, as far as eye is concerned, anything that looks like a parabola is a parabola, anything that looks like an ellipse is an ellipse, okay, and maybe something that looks like an ellipse is easier to generate than an ellipse. So when you want to generate something that looks like an ellipse, you need not actually draw the ellipse. You can draw something that looks like the ellipse. And this something that looks like the ellipse may be easier to draw. You understand? So you can cheat by images. The eye cannot say that this is an ellipse and that is not an ellipse. Anything that looks, any parallel curve to an ellipse like this will look like an ellipse, but it's not. The eye cannot see that. You have to write the mathematics and see that it is something different. But the eye cannot distinguish. Okay. So these kind of curves are very, very important. So you see this green and this orange curve, they are also parallel curves to the involute. This is a blue curve, which is again the original up to a translation. It is the original cycloid. But the point is that the green and you see the orange ones, they are not cycloids. And the important thing is, you see, you are getting many such curves. So you don't get only one involute, you get many involutes. So if you take the correct involute, you can get back the original curve. Okay. So I think I will more or less, I think you have. So let me say some interesting things. So the cycloid is one of the most important curves in mathematics and physics, okay, and it's called the Helen of geometry, and of course it has been involved in mathematical controversies, but I want to tell you three cases where the cycloid is the unique solution. So there are three types of problems. So of course I'm saying many things. I want you to go back and go to Wikipedia, for example, which has very good references. And then in the Wikipedia page, you will see references to many textbooks and many other materials. So there are three physics problems, physics applications. So the first thing is what is called as the, so let me call this, so the first one is the tautochrone problem. So what is this tautochrone problem? So the idea is the following. I want a curve, okay, which connects a top point to a bottommost point, okay, and if this curve should be such that if I place a bead somewhere here and make it to move along the curve, okay, so if I here is a starting point P, okay, at t equal to 0, and it comes to some t equal to t of p to reach B, then so what I want is I want this t of p to be independent of p. Okay, I want a curve with this property. What it means is that no matter where you put a bead, it will take the same time to come to the bottommost point. So what it means is if I put a bead here closer, and if I put one more bead, let us say here, okay, all of them if I release at the same time, okay, you see the blue one, the purple one which is closest, that has to go slow. The red one has to go slightly more faster, and the blue one which is at top must go faster, of course. But all of them, that speed should be adjusted in such a way that if I release them all at the same time, they have to reach the bottom at the same instant. Can you find a curve like that? So the answer is yes, there is a curve. The curve is called a tautochrone, and what is it? It is nothing but the cycloid. The cycloid is a unique solution. Okay. So this tautochrone comes from chronos, which is time, and tauto is same or equal. So at the same time, okay, it's a curve along which you push something down, okay, it will come down at the same time, and the solution is a cycloid. Okay, and here is I think I can show you an animation here. Yeah, so here it is. Here are 4 particles, 4 beads, blue, red, green and yellow. Okay, they are falling down. They are all released at the same time, and you see they all reach the bottom at the same time. And this curve is actually a portion of the cycloid. It's half the half rotation of the cycloid, right? And you can see this the distance time graph of these 4 curves, and the slope of that gives a velocity, right? So you can see for the yellow one, the slope is less. The yellow one is closest, so it goes slower. Look at the blue one, which is at the top. Its slope is highest. So it's adjusted. So see, the point is that the geometry of the cycloid adjusts the speed, so that no matter where you start, you will reach the lowest point at the same time. Okay, so that's one beautiful thing about the cycloid. Okay, then here is another problem. So I'll tell you 3 problems. Where did it go? Oops, all that disappeared. Okay, so this is another problem with my whatever I write suddenly disappears. Okay, so let me write here. So the next thing is the so-called brachistochrone problem. So this brachistochrone problem is, the following problem. I have a top point, okay, and I have a bottom point. And of course, in all these cases, there is gravity that is what is pulling things down, okay. There's uniform gravity. And basically the idea is find a curve so that, if you put a particle at the top point, it has to come along the curve to reach the bottommost point, and it should do it as quickly as possible. So this brachistos means quick, and of course chronos means time. So shortest time for a particle released at A to reach B. I want a curve like that. So you can think of all kinds of curves. See, I can think of course, the straight line. Okay. Then I can think of something, curved like this. So let me draw some more. I can think of something like this. Then I can think of something like this. And I can also think of something like this. I go down vertically. I do this, namely I go down vertically like this, okay, and then I go down up to some point, and here I make a small bend, and then I make it like this, okay. I have to put this bend here so that it can turn, okay, and now you can guess which is the curve that is going to give you the shortest path, okay. So there is a straight line, then there's along the straight line it's going to come down straight. Along the vertical line, the vertical part is going to come down at maximum speed, and then it's going to get curved, and then in the horizontal part gravity is not going to help, okay. And if you take this curve, what is going to happen is it's going to go down and then it has to climb up, okay. So the question is, you think which of these curves is going to go faster? What is your second one, namely this one? This is the one you think it is, okay, and not something like this, okay. So the answer is, and which you think will be the slowest? Yeah, so you see, it's very funny. It will be very counterintuitive. The truth is that it's actually this curve, which is actually the cycloid, which has which starts with this cusp here and passes through the point B. Okay, and even though it goes down and comes up, That is the curve. Okay, it's unbelievable. This is cycloid. The cycloid is a solution, and let me show you an animation. So this is very counterintuitive, and you should where is it? Brachistochrons here. So here it is. So you see, look at that animation. The one that comes along the straight line is the slowest. Okay, the second one that came down vertically and then went horizontally, that's not bad. Okay, the red one is the fastest and is completely counterintuitive. You must understand that. Okay, so you see, it's the shape of the curve that's playing the magic. And what is that red curve? That's again a cycloid. Okay, that's again a cycloid. Cycloid is also a brachistochrone. Okay, and it's very, very counterintuitive if you think about it. Okay, initially I used to think that only the straight line path is the shortest because it has constant speed, and then you see it's going in the same direction. Of course, in space, the shortest distance between any 2 points is straight line, right? The more if you divert from that, you have to travel more. And the cycloid, the red curve is, nobody will expect that to be the fastest. But that is a brachistochrone, okay? So it's very, very interesting. Then one final thing I wanted to say, which is the last one, and then I'll not take any more of your time. The last thing is the idea of cycloidal pendulum. Okay, so what is this business? See, all of you would have done this. You have this. You have a string, then you put a mass, and then you make a slight oscillation. Then it starts oscillating. What is the time period? T is equal to 2 pi root of L by G, where L is this length. Okay. Now again, is this formula correct? It's only for small oscillation. Again, it's the same old business, like the thin lens, thin mirror formula. Sin theta is made equal to theta, cos theta equal to 1 you do for theta small. Okay. What will happen if the amplitude becomes very large? It will start depending on the amplitude. Now in those days there was a problem. There was no advanced electronics or satellites available, but people were going on ships. And on ships, you see the ship will go this way, that way. And if you keep a pendulum on a ship, there's no way to avoid large amplitudes. Okay. So that means what? You cannot keep time on a ship. If you can't keep time on a ship, that means you cannot track the location of the ship. How do you track the location when you are in for example, how does GPS work? What happens is that in those days, of course, GPS was not there. But if you have a good clock, okay, then you can track the position on the earth in a very simple way. What you have to do is, you see, if you have a good clock, you know the local time. Okay. Then at that point, you see, with a good clock, you can keep track of time. At that point, I can look at the declination of the sun. I will know the latitude and longitude, so I will know the position. Because at every point on the earth at a given time, I know what is the latitude and at that latitude and longitude, I know the declination of the sun. Okay, so I can keep time. So what I need is, I need a good clock. But pendulum clock will not work on a ship. So what do you do? So I need a clock which, even if I make large amplitudes, it should keep the same, time period. So the time period should be really independent of the oscillation, the amplitude of oscillation. Okay. So this problem was solved by Huygens, Christian Huygens, the progenitor of the wave theory, right? So there is something called a cycloidal pendulum. So his idea was the following. What he did is, you see, what is happening when you take large oscillations, okay? It is the length of the pendulum that's creating a problem. So what you do is, as the oscillation becomes large, the amplitude becomes large. You cut down the length of the pendulum to adjust it in such a way that you still get a time period which is independent of the length of the pendulum. So what Huygens did is, he did the following thing. And again, the hero of the story is a cycloid. So what he did was, he took two cycloids like this, okay, and then he took, this involute of the cycloid, okay, and put a string here with a mass here. And what will happen is, as this pendulum moves, you see the effective length of the pendulum is becoming smaller, because it is cut out by this portion, okay. And then it was Huygens who discovered that this pendulum will be, time period is independent of the amplitude, okay. It's called the cycloidal pendulum, okay. And so this is, and so if you have several pendula of different amplitudes, they will all keep the same time. Their time period will not depend on the amplitude. And since they all keep the same time, they are called isochronous. So this is what is called as isochronous pendula. Iso is equal, chronos is time, okay. So Huygens found that you can do this, and again the curve that is responsible for this is the cycloid. So the cycloid has got such beautiful things. It is its own evolute. If you take the right involute, again it is its own involute, okay. It is a solution of the tautochrone problem. It is a solution of the brachistochrone problem. It is a solution of the isochronous pendulum problem. So let me show you an animation for that. That is where is it? It was here, I think. Not this. So here it is. So here you see there are 5 pendula. They are having different amplitudes, but you see they all keep the same time period. They all take the same time to go from one extreme to the other extreme, okay. And the beautiful thing is, the path that they trace is a cycloid, inverted cycloid, that is actually the involute of the cycloid at the top point, okay. And the lengths are constrained by these two, which are also cycloids, the same cycloid, okay. So that is the beauty of a cycloid, all right. And yeah, so I think I can stop up at this point. We have already you have to get along with your projects. Yeah, so I will stop here. Thank you. I advise you to go to wiki and look at all these things. See, there's a lot of math. If you are interested in calculus, you can get calculus proofs. If you are interested in geometry, you can use geometry proofs. A lot of material is available. You can read about this. And for all these problems, you can write out the physical equations and use calculus and show that actually the cycloid is a solution, okay. So you can do that. That's all for you, okay. So if anybody has any questions, please ask me. Otherwise, I will quit. Yeah. No questions. Okay. So thank you. Okay. So we will call it a day.
I'd like to take this opportunity. I'd like to take this opportunity to deliver the vote of thanks. So first of all, thank you, sir, for that beautiful lecture. I think that last animation there really proved your point about how beautiful maths can be and how we can apply it to solve real world problems. I'd also like to thank the RSIC management and IIT Madras for giving us this opportunity. Once again, a round of applause, please.
Yeah, thank you.